Hi and welcome to a tutorial over electron configurations of ions. Please have out your notes in a periodic table. We're going to review electron configurations first. Remember that electron configurations are the electrons in the outer energy level of an atom. We say they're like the front lines of an army because they're the ones involved in chemical reactions. Valence electrons are shared or transferred during these reactions. The number of valence electrons that an atom has is directly responsible for the atom's chemical behavior and its reactivity. I want to go ahead and remind you of what a segment of the electron configuration looks like and what it stands for. The number in front is the energy level, which correlates with the period on the periodic table. The letter is the sublevel or the block letter. And then the exponent is the number of electrons within that sublevel. So, the number of valence electrons can be determined from the electron configurations. What we're going to do is we're going to count all the electrons in the outer or the highest energy level for that atom. So starting with lithium, we've got 1s2, 2s1. Okay, 1 is a very low energy level. It's the lowest one on the periodic table. 2 is higher. So how many electrons are in that energy level? There's only one electron. So it has one valence electron. One electron in that outer energy level. Beryllium, 2 is the outer energy level with 2 valence electrons within it. For beryllium, 2 is the outer energy level. Now it's in the S and the P sublevel, so we have to add those electrons together. That's 3 valence electrons in the outer energy level. So this pattern continues. With carbon, we've got 4. With nitrogen, we have 5, oxygen 6, fluorine 7, and neon has 8. So for the dot structure for these, what you do is you just write the symbol. So I'm going to write all my symbols first. Okay, so you have a symbol, and then you represent with dots the valence of electrons. So with lithium, there's 1 valence electron. Beryllium, there's 2. So I like to put the dots opposite of each other. With boron, there's 3. So I kind of just go clockwise. With carbon, there's 4. Okay, after you have 4, then of course comes 5. But you go around once. And then at 5, you make your first pair. So the rule is at 4, you go around once. You should not have any pairs 1 through 4. But at 5, you'll see your first pair of electrons. Okay? At 6, we're going to have 2 pairs and then 2 that are single. For fluorine, we've got 3 pairs and then 1 all by itself to make 7. And for neon, you'll have 4 pairs, making a total of 8 valence electrons. That's just the pattern you should follow when drawing your electron dot structures. So the number of valence electrons for the representative element groups follows an easy pattern from 1 through 8, going across the periodic table from left to right. You should know this. Here's the pattern. It's easy. 1, 2, 3, 4, 5, 6, 7, 8. There is an exception to this, though, and that's helium. Helium only has 2 electrons. It's impossible that it would have 8. So helium, on some periodic tables, will actually be located above beryllium. Okay, notice that the elements in a group, also called a family, all have the same number of valence electrons. For example, group 1 elements, known as the alkali metals, all have 1 valence electron. Therefore, they will behave in very similar ways. So try this. Find an element on the periodic table that has the same chemical reactivity as sulfur. Here's sulfur. So this is very easy to answer. Any element in the same group will react the same. So oxygen is a very good answer for this. Here's a diagram of the electron dot structures for all the different atoms in those groups. So notice here that they all have the same number of dots, except helium is kind of the oddball. Like I said, it would fit nicely right above beryllium. Okay, so ions and electron configurations. So electron configurations for ions must be adjusted based on the number of valence electrons lost or gained to form the ion. So remember, ions are not neutral. Their protons and their electrons are not equal. Because they've either given away electrons or they've gained electrons to become stable, they are charged. So this impacts the electron configuration, and we'll talk about that in a minute. So calcium, it's a metal. Its electron dot structure would have 2 dots because that's 2 valence electrons. It's going to lose its electrons in order to form Ca2+. All right. Oxygen, on the other hand, is a nonmetal. So what nonmetals will do is they will gain electrons in order to form 8 electrons total. So if we look at oxygen, it is 1, 2, 3, 4, 5, 6, 7. It's going to have 6 valence electrons, so it's going to have 6 dots. It's going to gain 2 electrons in order to have 8. Now when it gains those 2 electrons, oxygen becomes negatively 2 charged. So it's important that you understand that. If you're gaining 2 electrons, you are gaining 2 negative charges. So therefore you become negatively charged. I'll do aluminum, and the others you should be able to do on your own. So aluminum is a metal. It's located right here. It has 3 valence electrons, so we'll put 3 dots around it. Aluminum, because it's a metal, is going to lose its electrons. It's going to lose those 3 electrons. And by losing those 3 electrons, it becomes Al plus 3. Okay? Try fluorine, potassium, and nitrogen on your own and check them with the key online. Now for each of the above elements, write the electron configuration for the atom and then adjust the configuration for the ion by losing or gaining the proper number of valence electrons. So if you look, I've written out these configurations for you. And all we have to do now is adjust them based on whether they've lost or gained. So oxygen, we just said that it is going to gain 2. So it's going to be negatively 2 charged. Well, if this is a neutral oxygen, it needs to gain 2. So it will be 1s2, 2s2, 2p6. You can also check, because in this outer energy level, now it has 8 valence electrons, which is very good. Okay, aluminum. We said aluminum is Al plus 3. This means it's going to lose 3 electrons. So if we look at aluminum as a neutral atom, in the outer energy level, it's going to lose 3 electrons. So it will also be 1s2, 2s2, 2p6 as an ion, having 8 valence electrons. So what's interesting is that these electron configuration for ions can be very similar for multiple atoms. Okay, and then we've got fluorine. So what does fluorine do? Fluorine is going to gain 1 electron. Right now, as a neutral atom, it ends in 2p5. So we've got 1s2, 2s2. When we add an electron, it becomes 2p6. This is interesting. 8 valence electrons, but right now the oxygen ion, aluminum ion, and fluorine ion all look the same. Okay, I call this noble gas envy, because what is the actual configuration if it's 1s2, 2s2, 2p6? Okay, that would be neon. So what's happening for these ions is when they gain or they lose electrons, they're going to look like noble gases. And the reason for that is because noble gases are very stable. And that's why ions are gaining or losing their electrons to become stable like these noble gases. All right, try the last 2 on your own and check the key online. Okay, so the last thing I need to teach you in this video is how to draw the transfer of those electrons to form a compound. So it says ionic compounds form when a metal loses electrons to a nonmetal and the resulting oppositely charged ions attract. With your teacher's assistance, make electron dot diagrams for the following pairs of elements showing how electrons transfer to form the compound. Then write the name and formula for each compound. So we're putting a bunch of skills together. You really do need to be able to do this. So let's look at calcium, for example. After looking at your periodic table, you can see that calcium should have 2 valence electrons. Okay, and fluorine, on the other hand, is going to have 7. So what's going to happen here is that calcium is going to give away its 2 electrons and fluorine is going to gain 1. So I want to show that happening. Here's my calcium and here is my fluorine. Because remember, when they are happy, they have 8 electrons. So calcium gives away 1 electron to fluorine. Well, calcium's still not happy though. It has that extra electron. So what happens? Another fluorine is there to pick that up. So calcium donates 1 electron to one fluorine and its other electron to a different fluorine. That's why the compound for calcium fluoride is CaF2 because of this bonding formation. Okay, and we call this an ionic bond. So it's CaF2, known as calcium fluoride. Okay, let's look at the next one. Sodium and nitrogen. So sodium is Na, it has 1 valence electron. Nitrogen is just N, and it has 5 valence electrons. So again, sodium, because it's the metal, is going to give away its electrons. Nitrogen, as the nonmetal, is going to gain electrons. So we're going to put nitrogen in the middle here. If I have 1 sodium, this electron from sodium can pair with that nitrogen. Well, nitrogen's not happy. It doesn't have 8 yet. It now has 1, 2, 3, 4, 5, 6. It needs 2 more. So there's another sodium with another electron to give away. Well, it still needs 1 more. So there's another sodium with another electron to give its electron away. That's why the compound between sodium and nitrogen is Na3N. 3 sodiums for every 1 nitrogen. This is known as sodium nitride. Go ahead and pause the video and try number 3 on your own. Okay, welcome back. Hopefully you had success with number 3. Here's the answer for number 3. So the dot structures for aluminum, it has 3 valence electrons. Oxygen has 6 valence electrons. Aluminum, as a metal, is going to give away its electrons to oxygen. So this one's a little bit messy if you look at my compound formation. But you could also do a little cheat and crisscross your oxidation numbers to know aluminum as +3, oxygen -2, so that they're going to form in a ratio of 2 aluminums for every 3 oxygens. And this is known as aluminum oxide. I hope you found this tutorial to be helpful. For more help, go to our website and look at the key online. Have a good night.